This is video help for problem 10.3. In part A, we start with the laboratory precession frequency. We've got our main magnet, but then we've added a gradient. And so our frequency changes from one Z to another. And at a particular frequency, we would excite all those protons or whatever at Z. Well, of course, our frequency will be spread. We'll have a bandwidth, and that bandwidth then will mean we'll have a spread in delta Z. Take a change in F, the only thing that changes is Z. So I've got this relationship between the bandwidth and delta Z, and that will give me a slice of thickness delta Z. In the numbers, there are some things for you to check against in the written homework hints. In part B, we talk about a uniform delta Z excitation. That means we'll need a uniform bandwidth. We'll need a uniform spread in frequency. There's our boxcar again. So we would have a boxcar, for example, of F over delta F, so that the frequencies would lie between minus delta F over 2 and delta F over 2. I'm leaving the main Larmor precession and the gradient precession at some Z position, Z0, and this will be then the spread that will give me a slice that's centered at Z0. Well, so this will be an overall envelope times just a central sinusoid. Well, what is that envelope? What is the dependence of time that our pulse, our B1, this is the guy exciting the protons, the transmission, the transmitted pulse. What is its time dependence that gives that frequency? That's a Fourier transform. So you know that a Fourier transform, going back and forth, this is my distribution in frequency, then I'll get a sink in time. And actually I know this is within a constant, and actually the constant I think is just delta F. The Fourier transform, that'll give delta F times the sink of this. And our sink is what we're studying here. We're interested in where this vanishes. In time, we've got this main peak at t equals 0. Where are these zeros? Zero crossing. Where does the sink vanish? Remember, it doesn't vanish at t equals 0 because that has a denominator at 0 too. That's where it's actually in the limit, this big number. But this will vanish whenever this argument is multiples of pi, 1, 2, 3, also negative, see, on the other side. But the first zero crossing on the right then is at some time t1, 1 over delta F, because then that'll be pi, that'll be the first time it vanishes. The next one would be 2t1, and the next one 3t1, just from corresponding to n equals 2, n equals 3. Well, what you can do, if I define the tau or RF as really the half time of the pulse, say all the time from the 0 to the right, however far out we go, let's suppose, because actually in reality we're going to have to truncate this. We're not going to have we can't let the this pulse time run for a long time. I just take this time here, divide by this incremental t1, and I'll get the number of zero crossings, the number of n values I get. On the right, this is a notation that says whatever's inside here, this notation means the biggest integer that's not greater than it, less than or equal to it. That'll be the number of zero crossings on the right. If you want to count the zero crossings on both sides, just multiply it by a factor of 2. There's a footnote on the page or the preceding page, depending on which edition you're going in. Well, that is interesting. We want to know where those zeros are because that's the way we're going to ultimately make a pulse in the laboratory. And the last thing is, what happens if you change the gradient? Well, you change the gradient, you're going to change the delta F. You change the delta F, you're going to change this first time. You're going to change the first time, you're going to change the basic time step in your calculation of the number of zero crossings. And that's a pretty quick